Result plus our latent yes with that.
Good morning. Welcome to the third day of Statistics and Exoplanets. It's wonderful to see you. And I guess it's too rainy for the beach today. Suzanne and I have two announcements. I'll start with one. This has not been publicly announced because it was just approved a couple of weeks ago. But something called the SAMSI Institute, Statistics and Applied Mathematics Sciences in the United States, is going to run a year-long program for astronomers and statisticians to do research together in North Carolina. And in particular, there's going to be working groups lasting for several months with a lot of travel money and even salary money available to young postdocs and grad students to come to North Carolina to work with statisticians on exoplanetary methodology. In other words, not the data analysis, not the astronomy and astrophysics, but those of you who are interested in time series analysis and in difficult problems that are encountered in modeling, Bayesian modeling, for instance, of systems, this is the kind of issues that will be done. So if you're interested, starting in 2016, it's a year from now, it's not now, starting in September 2016, the leader of it is Professor Joe Gishlebu, statistics, who's sitting there. But if you don't know his email and you happen to know mine, you can email me, I'll pass it on. And if you're interested in working with statisticians, even possibly getting salary to travel, travel for sure, maybe salary, contact us about the same thing.
Okay, and my announcement concerns the hack day or speaking session tomorrow. If you're presenting something in the morning, you don't need to upload your presentation in the speaker room. In fact, you can't. You can bring your own laptop, or I will have my Mac laptop, and you're welcome to upload something to that. Okay, and now I'll hand over to our chair for this morning, who's behind you.
Thank you, Suzanne. So we will hear the first speaker of Jenkins.
Good morning in TV land.
Okay, good morning, everybody. Can you hear me? Yes. All right, so I'm going to talk about the transit engine, Kepler, that we've been modifying and improving over the last several years, and about machine learning approaches to identify likely candidates in transit surveys. Louder.
Yeah, Mike.
All right, is the mic on? Everybody hear it?
You can take it off the mic.
Okay, I will take it off. Okay, so here's an outline of my talk. I'll give you an overview about how transit planet search works in our pipeline. Talk about chi-squared vetos, which are secondary tests to eliminate false alarms. I'll talk about a new diagnostic called the statistical bootstrap. And I think it's really going to be key in helping understand light curves and partial requesting events and transit features. And then I'll talk about machine learning stuff. So this is our pipeline, and I will not be talking about pixel level calibration, nor fundamental analysis, nor will I talk about research data conditioning. All of these upstream pipeline components have experienced a lot of change, modification over the last year and a half especially. And I'm really excited about all those changes and how they're going to improve the light curves for Kepler, for light star time, for all kinds of astrophysics, as well as for pushing down to smaller planets and longer period orbits. Today I'm going to focus on transit planet search. The bootstrap belongs in data validation mainly, and I'll talk about how today. So to motivate this, back 20 years ago I was asked by Bill Ruki to try to tackle the problem of star spots. And the only star for which we had good enough measurements to ask the question, can we detect Earth-sized planets transiting across sun-sized stars was to look at the sun. So this is 3.5 years of SOHO data. And irradiance or brightness is on the y-axis, and we've got about 3.5 years here. And of course, we've got these pesky things called sunspots, which are our noise, our trash, but other people's treasure. And as time goes on, you can see this data set started in January of 1996 near Solar Min. As time progresses, there are more and more star spots like the ones seen in these images. And they cross the face of the star and impute drops in brightness that actually are quite strong compared to a transit of an Earth-sized body, which is the size of this image of an Earth-sized body. So star spots can make deeper transit-like features than transits. Well, how do we solve this problem? If you look at that light curve, you can see that it's not white noise. And so we drew a page from detection theory developed first in the 60s. How do you detect deterministic signal with non-deterministic parameters against colored Gaussian noise? And this proved to be pretty good at modeling this our sun's variability. And how it works is that essentially we have noise W, and X is the data that's composed of noise plus possibly the signal of interest S. Then what you do is we formulate a detection statistic that essentially is the dot product of the data against the signal mediated by the inverse autocorrelation structure of the noise. And so it turns out that this is a coordinate transform. If you solve for that coordinate transform, the square root of our inverse essentially is H. That's known as the whitening transform, the pre-whitener. And so you can then establish two variables, X tilde and S tilde. So you've transformed a difficult problem into a simple one because this is just a matched filter. And if S is stationary and it should be Gaussian at this point, then the bottom is just the normalization term signal. It's just an estimate of the noise. We can transform this under the assumption of stationarity into the frequency domain. So now you're working with power spectral densities as the Fourier transform of the characteristic function. And that's very convenient because there are very powerful FFT-based techniques for doing joint time frequency analysis. And wavelets is one of those. That's the one we have to choose. So what I'm showing here, though, is the energy or power density as a function of time scale on the x-axis. And the curves that go up to the right are what you see in terms of what the sun is doing at high solar activity in the red and at low solar activity in the orange. So the distribution of power changes, and most actions at time scales longer than a day or so. And at short time scales, there's not much action. So that shows that our sun, on time scales of hours, is basically about the same all the time. The other curves here show you how the energy is distributed
in transit pulses that are either 8 hours or 12 hours. So where we have the chance and opportunity to detect transits is where the energy in transit is above the power in the observation noise. And you can accomplish that by observing transits that are either deep enough to permit this or to look at a sufficiently large number of transits to make the composite signal deep enough. So it's the separation in frequency or time scale that allows us to distinguish planetary transits, which are short, against spots, which typically occur for stars like the sun on timescales of weeks. Well, this is a relatively simple implementation of a filter bank, and this is how we implement it in the pipeline. And essentially, let's see if I can figure this out. Yeah, so what we're doing is we're decomposing the input time series into a bunch of different bandpasses. Here are the responses of the bandpass filters. It's an octave wavelet decomposition, so you have a high frequency component that's half the Nyquist, and you've got a quarter, then an eighth, all the way down. So you go from high frequency down to low frequencies. And in each of these channels, then you estimate the noise power. So we actually pretend that the noise in each of these channels is white, the time variance. So we estimate the noise power as a function of time, and use that to then whiten the data. And then we correlate that against the counterparts coming in on the right for this similar wavelet decomposition of the transit pulse of interest to us. We combine those together via convolution and sum them up to establish the transit statistic or detection statistic in this whitened data state. And it's really simple, it's really fast. We do not decimate our wavelets. They're overcomplete, that's to preserve shift and variance, which is a very nice property, because then you only have to pass one signal pulse or transit pulse through your system. And it's kind of like a graphic equalizer, actually. We're just tuning the knobs in the graphic equalizer to flatten the noise power approximately across the full spectrum. So this is the sum of data with noise added to represent what we thought Kepler would deliver in terms of instrument and shock noise. And we've added 4 transits of an Earth-sized planet. And when we whiten the data, the blue is with the transits. You see these 4 peaks here occurring when we expect them to occur, given what we know about the injection. And the red is without transits injected. When we fold that over all the trial periods, you see a significant spike at the actual period, and you see aliases, because at every particular period, there's some phase in which you pick up some of the transits. Anyway, this is what allows us to find these small planets. And then you can look at the phase and see when the first transit occurred. So this is a very pretty picture. It worked great. It's real data, but it's not Kepler data. This is real Kepler data. It's just an illustration of how this works. This is a real-time series, 1 quarter's worth of data. This is cadences, so about 49 per day. 3 months of data. Here's the whitened flux. What I'm going to show you now is an illustration of the fact this is an adaptive system. So what I've done is I've smushed together 6 impulse responses. So I've added impulses to the original data, and then I've extracted the effective impulse response of the system as a function of time. So you see, as the noise characteristics change, the impulse response of the system changes. So it's adapting to what the noise is doing in order to conform but under the assumption of color Gaussian noise is an optimal detector. Well, real life isn't as pretty as all that. And so we needed to find ways to beat down false alarms from instrumental systematics, radiation events, sun sensitivity dropouts, and astrophysical things, flares, stellar variability that's not well modeled as a broadband colored Gaussian process. So one of the first things that we did was to use a robust version. So this is a kernel-based approach to D-white outliers. So it's essentially the same kind of statistic, and it's in the same units, but it's mediated by a weighting matrix that is just a kernel-based approach to robust fitting. So if there are no outliers, then this statistic will be very close to the linear statistic we formulate first. But that proved not to be good enough. So Sean Cedar actually brought in some technology from LIGO, and you can break the data into different pieces and say, is the contribution of each piece consistent with what it should be given my understanding of the noise? So in this case, what we call chi-square 2, please look at this paper, is to look at the contribution from each transit to subtract off the expectation, and then you can transform this into a chi-square variable with n minus 1 degrees of freedom, where n is the number of transits. And in fact, this statistic has the same properties under the null hypothesis as it does if there are transits there. So that makes it a statistic allows you to say, is this data wonky in some way? So that's proved to be very useful. And then the goodness of fit is a similar statistic, but instead of looking at individual transits, you're looking at individual data points. So you're looking at the residuals from the fit implied by the match that you've accomplished. But again, it has its chi-square with number of points in transit minus 1 degrees of freedom. So again, another filter. Well, what does this do? Talk about that in just a moment. We've made many other improvements in TPS. One of those is to use rounded, darkened transit-like shapes for the search rather than box shapes. That buys us a few percent in sensitivity in terms of better correlation with the actual signals we're looking for. It helps a little bit. We've applied astrophysical limits on the period and duration for the search space. Why search for planets with durations for a given orbital period for a star that don't make any sense, right? And we've been constantly refining the vetoes and tuning them to maximize sensitivity to real planets while reducing the chaffs to a survivable level. Because it's not cheap to do this kind of search and all the subsequent data validation. Well, while these vetoes have proved indispensable, you're making additional cuts. And so you inevitably impact the sensitivity. And so just for giggles, if we don't have the vetoes, we generate about 126,000 threshold crossing events or translate features on 200,000 targets. That's a lot of stuff. And all but about 6,000 of those are not interesting at all. So you can turn the vetoes off, and this shows, this is a 2-year-old plot. But the blue is ideal behavior. If the white were perfect, then you would get the blue. You would inject transits and you would recover them at this rate as a function of this SNR. But we don't. We get, without filters, we get the green, which is actually pretty good. It's not perfect, but it's pretty good. But if you turn the filters on, you get the red. And so it slides to the right. You're reducing your sensitivity as a cost of reducing your sensitivity to the stuff that aren't transits. So you have to, you're taking a cut. The reason why is because we've got the wrong model, right? It's not really a binary hypothesis problem. It's a multiple hypothesis problem. We're trying to catch up after the fact because there really are multiple scenarios out there that impact the data. Then it's going to reduce the sensitivity. So we will never achieve the blue curve, never. But we're going to get as close as we can. So another partial explanation for why the green curve isn't coincident with the blue curve is that we're pretending for this analysis that the three lightnings are perfect. We perfectly understand the correlation structure as a function of time for each and every light curve. That's simply not the case. Well, there's something we can do about this in terms of trying to understand what's happening. And that is that you can see how often you pull a rabbit out of a hat. And so the nice thing about what we're doing is that you're adding together random variables that come from the same distribution. So what we do is we take the out-of-transit data and we formulate the single event statistics that encapsulates the correlation structure's impact on the detectability of the transit as a function of time. We scramble those up, put them in the hat, and then for a 4-transit case, we draw 4 times from the hat, formulate a multiple event statistic. We do that over and over and over again, at least in the thought experiment. We look at the distribution of those multiple event statistics and ask the question, how likely is it that I would have drawn an event by chance through this process that has a mass or a detection statistic as high as the event that I just found? And if the answer is very small, then you're very happy. If the answer is very big, you're very unhappy. So that's what we're trying to do. Now, it turns out that you can simplify this. You don't have to draw out of a hat like this. You can actually model the distribution. If you have a model for the distribution, you can know that all you need to do to get the M transit distribution is to combine these together, because the draws are uncorrelated. You can translate this to the Fourier domain and simply then raise the Fourier transform of the single event distribution to the power representing M transits and then translate it back. So here's a graphical illustration of this. This is the normalization term on x-axis and the correlation term on the y-axis, and this is the distribution of the single event statistic in this space. It's a binary distribution for this target, 8311864. And so we raise this to the 4th power, and lo and behold, here is the 4-transit statistic distribution. So you take this, You divide the correlation component by the normalization component, you count up the number of events in your bins, and then you get this, which is essentially a histogram, but it's a very fine histogram of the log of the false alarm rate implied by this experiment as a function of the multiple event statistic. In this case, with only 4 transits, we can't actually, the bootstrap doesn't reach all the way out to 9.7 sigma, but we can fit a Gaussian to this distribution to estimate that the false alarm rate for this particular signature is below 10 to the minus 15, which is well below 10 to the minus 12, which is kind of the canonical cutoff in Kepler, given all the statistical tests we're doing across all the stars. Okay. Well, we can look at this statistic. This is the bootstrap for roughly 16,000 threshold crossing events found in quarter 1 through quarter 16. This is false alarm rate, log false alarm rate versus the mass. They're color coded by whether they're confirmed or validated planets in cyan, stars, false positives, which are red X's, and planet candidates, which are green plus signs. And then everything else that never made a KLI is in blue. You see there are really 2 distinct populations, very strong populations. One that follow this curve that actually the left envelope here is what you would expect if things were ideal. That's very important because it tells us that the Whitener isn't perfect and that the bootstrap is telling us that actually the noise power is a little bit higher than we think. So that means when you have a 7 sigma event, it's a little bit smaller. When you have an 8 sigma event, it's a little bit smaller. So this probably explains in part why that green curve was not as close to was not perfectly coincident with the blue curve. Your detection statistics are not quite as high as they really as you think they are. So the bootstrap allows you to recalibrate those and say, well, I got a 9 sigma event, but if you're up here, it's really a 2 sigma event. Now this population of stars, light curves, has a very flat false alarm rate that's very high as a function of events. And if you look at these light curves, you find that there's all kind of interesting things happening on these light curves. Some of them are flare stars with loads of flares. Some of them are just junky light curves. Some of them can't even see a star. At any rate, this is very useful for understanding whether a TC might or might not ever become a KLI, become an object of interest, and that is just by looking at the fact that you can do a kind of prosecute. And we don't do that kind in the pipeline. Another thing you can do is you can say, based on the bootstrap, what should this threshold happen to maintain the false alarm rate that you wanted to maintain in the first place? So this is the bootstrap threshold you get out of that experiment versus the log at the false alarm rate for each TCE. And you see basically that there's nothing above about 10 sigma in terms of the threshold you should have applied that was ever confirmed or validated, or indeed almost never became a KOI or planet candidate. This is an interesting point. This is Kepler 90d. This is in a system of at least 4 planets with very strong TTVs. So about 26 hours. So that means that when we subtract off the transits, which you do for all the planets you found, all the planet-like signatures you found, there are transits left because we assume a perfectly periodic transit pulse train. And so this is higher than it should be because there are transits left in there and they pollute the statistic. But this is the most egregious case. And it still has a false alarm rate that tells you that you shouldn't worry about it too much. So that's the second section on Díaz and bootstrap. What I want to turn now to are some very exciting results in machine learning techniques applied to the diagnostics we get out of data validation. So this is a summary report out of data validation. There's a lot of information in here. So you can see a lot of plots and a lot of numbers. There's a full data validation report underlying this that's about 100 pages long. And if you printed all of them out, they would be about 140 stories high. So I hope nobody ever tries to do this. We wait a long time at the printer. And I don't know how you stack them up and keep them stacked up in the wind in Chicago, right? Anyway, that's a lot of paper. That's a lot of information. And struggle as we might, I don't think that any group of humans could actually really ingest and understand all of the information in all these reports for all of the transit-like features that are found. But is there a way that we can try to take into account much of this information that humans can't? And so this is a problem because we have a plague of planet-like signatures. If everything were groovy, we would find the planets and nothing else. Maybe close binaries. Some people care about this. But the fact is that we have this situation that Jesse Christensen and Steve Bryson both talked about, and that is that this is Q1 through Q12, and this is the Q1 through Q16 surge. And we see this large spike near the orbital period of the spacecraft. These are caused by image artifacts, electronic image artifacts. I'll be happy to answer your question about what's causing them, but it's something endemic to the hardware. And it's injecting very small translate signals into the data, but it happens about the same time every year. And so we get a lot of them. So how can we recognize these guys against the real things? We're making great progress both with human-based vetting, which is now turning to robo-vetting. There's some great posters about that. The effort we've been doing for the last couple of years is to use random forests. So I'll tell you just a little bit about how those work. These are random decision trees that each decision tree is trained on a random subset of the training set population you furnish. This is a supervised machine learning system. And each node in the tree is trained with a random subset of the attributes. So each tree then is basically independent of the other trees from a statistical perspective. As individual classifiers, they're relatively weak. What you do is you train a lot of these trees. And you keep on adding. So you might train 1,000 trees, you might train 10,000 trees, you might train 100,000 trees. And they have very nice properties that they allow you to assess the importance of each attribute, so you can decide whether it should be included or not. And you can use the voting record to score the objects classified as planet candidates and the other categories that you include. And perhaps most importantly, you're able to overlay on top of this, a Bayesian classification scheme allows you to estimate the posterior probabilities for each class. So this is the result of training on Q1 through Q16, and the red are basically bananas. These are things that don't look like transits or clips and binaries. The green are things that look like black clips and binaries or astrophysical false positives in our lingo. And the blue are things that are either confirmed or validated planets or were previously identified as planet candidates by TSER. So we're trying to leverage the long history and loads of effort, I mean, many, many decades of pushing years of human effort to try to come up with a machine learning approach that makes this job a little easier for the humans so they can focus their attention on the most interesting objects and not spend all their time on the 15,000 or so junky things. And this, let me just explain briefly, this is the planet candidate vote fraction. So each tree gets a vote, it gets to vote whether it thinks an object is a planet, an astrophysical false positive, or a non-transient phenomenon. So you get a vote fraction, but since they all have to sum to 1, it's a two-dimensional plot. So we can then look at the distribution of the blue, the red, and green to try to understand what the posterior probabilities are. In terms of this particular experiment, this is the confusion matrix. You see we basically are getting pretty good results, so an overall misclassification rate of about 5% or so, which is pretty good. And really a fairly good agreement with human vetting results as well. Well, anyway, what we do is we then look at the density of the red points on that feature space, vote fraction space, and look at the density of the blue and the green, and these then are conditional densities in that feature space that together with the prior probabilities of each class then can be used to identify the posterior probabilities, in this case for the planet candidate class. So you see that you have very high posteriors up near the planet candidate vertex, and then very low posteriors close to 0 near the other two vertices. And you can do this for each class. This is a false color image, and red, green, and blue are convenient. For planet candidate, astrophysical false positive, and non-transiting phenomenon. We're very excited about this work. Certainly, it's a lot of effort to get this together. My colleague Joe Tanzwright is now working on applying this methodology to Q1 through Q17. He's had a lot of interaction, a lot of collaboration with the folks like Jeff Hoffman who are using the RoboVetter. Nice thing is that we can add additional diagnostics furnished by people in the science office like Susan Mullally to this mix to help improve what we're doing, and then we can learn from each other. That's going very well. But this is a plot of, this is orbital period, not log orbital period. Fantastic for helping to do that. And this is the planetary radius, log planet radius. And then they're color-coded by the posterior probabilities. So you can see that out of long periods, you generally have lower posterior probabilities, but that's consistent with the fact that these are low-res and are objects and are not as reliable. What Joe has done, if you go to see his poster, is that he's taken these reliabilities and used these to weight the likely planet candidates coming out of this analysis to inform occurrence rates. So this is a plot of occurrence rate in periods down here in days, 50, 100, 100, 200, 200, 400. And then the fraction of stars with planets in each bin. So he's broken this down into 1 to 2 Earth radii, and then larger planets down there. So I think this is really exciting. I don't think that we want to be in a situation where we're calculating occurrence rates and we have an all or nothing for the candidates. As we push down to smaller, more terrestrial sized bodies, inevitably, we're not going to be as certain about those. And I think we need a scalar quantity rather than a binary quantity for the occurrence rates. Otherwise, you might be in a situation where you're very sensitive to your choice of what goes in and what is not in your catalog. So I do want to point to other very interesting topics and posters. I hope you all saw these, but if not, please go catch these folks because they're doing very interesting related work, including a different semi-supervised approach by Ahmed, auto-bidding by Jeff Coughlin, and then the Malalis have posters as well. So this is my summary, and I'll take questions this time.
Thank you very much. Questions? Thank you. I'm curious about the filtering process. When you do the filtering process of the line curve, you decrease some energy to some specific frequencies. That's what you're doing when you filter this out. So, assuming that the transit is a kind of infinite number of frequencies, it's very sharp signal. How much do you affect the shape or the amplitude of the transit when you do that?
Right. Well, that's a very good question, PDA. So the nice thing about this approach is that it takes into account the distortion of the filter on the shape of the transit. So that's accounted for explicitly in formulation. But what it's telling you is that the signal power in the distorted transit is what the noise is doing to your transit. Because if you have no noise, you have infinite SNR, right? So that's one nice thing about this approach is that it actually gives you an estimate of how strong your signal reference signal is. But that's accounted for explicitly, and we can look at individual examples if you wish.
Other questions?
A quick comment and a maybe detailed question. The comment, I absolutely love that you're considering the scalar quantity from 0 to 1. And I totally agree that that's going to be very important, particularly in the sparse regions of the theory radius diagram. A question about your false alarm rates. On your slide, I think you showed a number of non-candidates that nonetheless had exceptionally low 10 to the minus 100, something false alarm rates. Is that something that I should be concerned about? Is that some weird pickup? Am I misunderstanding?
Are you talking about the bootstrap?
Yeah, that's bootstrap.
Okay, so the bootstrap diagnostic is not aimed at telling you whether you actually have a transit. It's telling you whether a signature that you look like the one that you picked up on is rare or not. So that's really its purpose. But it should give you a good result if you just trip down the stairs 3 times at the same period. But if that happens a lot, then it'll suppress the false, it'll increase the false alarm rate, the false alarm rate. Let's see if we get back there. But I don't think it's a worry. These are what humans have done in terms of what they've decided. And indeed, most of the objects in this category are objects that look interesting in some way. They're closing binaries, or there's some kind of periodic phenomenon. Things up here are interesting, but they're interesting for other reasons that have nothing to do with the closing binaries or things that look like that.
A last question. Okay. There.
I'll put in a plug for the Hack Me. Come join us in sunny Northern California, where the humidity is quite low. For exoplanet population Hack Week in October. Natalie maybe put this up. I hope you all can join us.
So Jesse Richardson has a little set of simulated planets and set signals and things. Are there any thoughts on using that as part of the training set for just reinforcement?
Wonderful question, Tim. The answer is yes. Right now, Díaz right has started using the pixel level transit instructions as a training set for the auto better for this. And he doesn't have results yet that I'm willing to talk about, but he's going to let me talk to him offline.
Okay, let's just thank again the speaker. And we move to the next speaker, Leslie Rogers.
Hi everyone.
Hello to the internet.
Hey, good morning. I'm delighted to be here today to talk to you about combining transit and radial velocity data sets. So the planets detected both in transit and through radial velocities or transit timing variations are especially valuable because with the planet radius measured from the transit depth and the mass measured dynamically, together combine to give the planet density and some handle on ball compositions. So why should we care about planet ball compositions? Well, in addition to fully characterizing to the best of our abilities the properties and nature of the planets in their current form, planet ball compositions also give us some insights in the past formation and evolution history of planets. So in a coarse sense, we can divide the planet building blocks, or the ingredients that go into forming planets, into three main categories based on their condensation temperatures. There's the hydrogen helium gas, the volatile molecules, astrophysical ices, and then the rocky refractory material. The proportion of ice relative to rock in a planet gives us a tracer of the formation location of the planet relative to the snow line in the protoplanetary disk. And the proportion of a planet's mass in hydrogen helium is a tracer of the timing of formation relative to the disk dispersal lifetime. And it also gives us some signatures of planet photoevaporation that can sculpt the compositions, especially low mass planets. So this is for single planets. If we have multiple planet mass radius measurements, then we can look towards what are the dominant composition trends in the outcomes of planet formation. How much scattered is there about those dominant mass radius trends? And is there any evidence for distinct compositional populations that could be linked to different planet formation pathways? So this link between the compositions of planets observed today and their past formation and evolution history helps to motivate the tremendous observational effort that's being devoted to the radial velocity follow-up of transiting planet surveys, as well as transit follow-up of radial velocity detections. So in my presentation today, I'll be focusing on this explosion region down here, on kind of the nitty-gritty of how we go from planet mass radius measurements to insights into the composition of planets. In the first part of my talk, I'll focus on compositional insights for individual planets. And in the second part, I'll move on to planet populations. Okay, so how do we translate from a noisy mass radius measurement of an individual planet into insights into that planet's ball composition? Well, for that we can apply a Bayesian framework in order to combine the observational uncertainties, model uncertainties, and inherent degeneracies together in a robust way. So here I'm showing essentially Bayes' theorem adapted to this particular problem. So here I'm denoting by x sub I essentially the planet composition. So I'm using x sub I to represent a mass fraction in whatever ith ingredient of the planet composition you're considering in a given model. And so on the left-hand side here, we have the posterior probability distribution, a joint probability distribution for the planet mass and composition, conditioned on the radial velocity and transit data denoted by D, and whatever additional insights we're bringing into the problem, denoted by script I. Then here we have the likelihood of the true planet mass and radius, or of the data given a choice for the true planet mass and radius, which here are being treated as latent variables. And so here we can sample. We've already had several talks in this focus meeting about the analysis of transit and radial velocity data. So we can essentially sample from the posteriors of those transit and radial velocity data analysis to get the likelihood of the data given the mass and radius. This factor is where the planet interior structure modeling comes in, and I'll come back to that in a moment. And finally, here we have the priors. Here I've denoted it as a joint prior of the planet mass and radius. And of course, if you're only interested in the composition of a given planet and not on correlations between mass and composition, you can marginalize over the planet mass. So now, let me come back to this factor for the planet interior structure and evolution models. So here I've expressed it as the probability of the planet radius given a mass and composition. So planet interior structure and evolution models provide us with a forward model mapping planet mass and composition to radius. And it may also depend on planet age, flux, dollar parameters, whatever else you want to include in the model. So in most of the compositional bulk composition inferences that have been applied, this function has been assumed essentially to be a delta function defined by a forward model. We've essentially been placing complete faith in our models, and eventually we may want to solve that assumption. Or you could have essentially a generalized delta function that's marginalized over these nuisance parameters of your model. Now, there are many planet mass radius relations in the literature that one can use to define this mapping. And what I'm presenting today, I'll be using the mass radius relationships that I've calculated. And in particular, for planets with hydrogen helium envelopes, I'll be using mass radius relationships that have been calculated by Howard Chen. He's a rising senior at Boston University, and we've been working together to extend the mesostellar evolution code to be better applicable to simulating the evolution of hydrogen helium envelopes around low mass planets. So his paper will be coming out soon, and when it does, we're hoping that these adaptations to MESA will allow it to be a valuable tool for the whole community to use in simulating the evolution of hydrogen helium envelopes around low mass planets. Okay, but an important thing to note about this mapping from planet mass and composition to radius is that it's not one-to-one. So for any mass radius pair, there's a range of planet compositions that will be consistent with that mass radius point. Like even taking the coarse compositional ingredients that I mentioned before, gas, hydrogen helium gas crystallizes, and rock, that's already 3 components in a rather simplistic model where you only have 2 observational constraints, measured mass and radius. So you're left with a one-dimensional degeneracy, which I'm illustrating here for the example of GJ 436, a transiting exo Neptune. So here on this trinary diagram, I'm denoting the range of compositions that are consistent with just a point estimate of the planet mass and radius. So taking a radius of 4.22 Earth radii and a mass of 23.17 Earth masses. And here on this trinary diagram, the mass fraction in each component, be it hydrogen, helium, rocky material, or ices, is just given by the perpendicular distance from this shaded region to the appropriate component. So as you can see, while the mass fraction in hydrogen helium is relatively well constrained to lie between around 4% and 14% of the planet's mass, the rock to ice mass ratio is essentially unconstrained in mass by the single mass radius point. And so the presence of these degeneracies means that in inferring single planet compositions from measured mass and radius, or from radial velocity and transit data, requires that you assume matter. And whatever assumptions that you impose to restrict your model, whatever choices you make there, also matter and influence the outcome, your posterior probability distribution. Now, all hope is not lost, because we can be clever and try to answer the problems that are the lowest hanging fruit, that we are most sensitive to. So for instance, for volatile rich planets with hydrogen helium molecules, the example of GJ436b illustrated how we're most sensitive to constraining the mass fraction of a planet in hydrogen helium, whereas we're less sensitive to addressing questions like the ice to rock ratio, or even the degree of differentiation and mixing within the planet interior. In a similar way, for rocky planets, based on mass radius alone, we're most sensitive to constraining the total iron content of the planet. But the mass radius relationships are just less sensitive to the degree of differentiation within the planet interior or the oxidization state of the iron, how much is incorporated to the planet. Okay. So I've given an overview of how we can apply Bayesian techniques to infer single planet composition constraints. Now let me provide you with one example. And for this, I'll take a Kepler 36 planet system. And I'm cheating a little bit here, simply because these planets' masses are not measured by radial velocity, instead by transit time calculations. But I chose the system as an example because Kepler 36b, this inner, smaller planet in this system with two known transiting planets, is the likely rocky exoplanet that has the best constrained density in composition to date. And so these record-holding density constraints come from the influence of detectable solar-like oscillations in host star, gravitational interactions between the two planets that perturb their transit times, as well as dynamical stability considerations. So I've been collaborating with Jack Bluesauer and Josh Carter to revisit this planet system to see how much better can we constrain the planet properties, given the longer time baseline of Kepler data released since the initial discovery papers. And in the end, we constrain Kepler 36b's mass to 4.2% relative uncertainty and its radius to 1.8%. So here, these red regions are showing the posterior probability distributions of the planet mass and radius on this mass radius diagram, with other exoplanet discoveries shown in black. From the back, you can probably just see a red blob, which is effectively the 3 sigma uncertainty region, whereas these black points are 1 sigma. So that just illustrates how precise these measurements are relative to other planets. Now let's focus on Kepler 36b, this little guy. And one thing I want you to know is that the mass and radius posterior distribution is correlated. And this is due to the fact that the uncertainties in the stellar parameters make a large contribution to the uncertainties in the planet mass and radius. And since the star is constrained by extra seismology, the stellar density is better constrained than the perpendicular stellar mass radius vector. And as a result, we get these correlations in the planet mass and radius. For us, that's a good thing, actually, because it works out that these correlations in the planet's mass and radius, why the long axis lies roughly parallel to the mass radius relationships for constant compositions. So this helps us to further refine the composition constraints on this planet compared to what we would achieve if we neglected the mass radius correlations. And so here's what we obtain when we couple the mass radius posterior distribution from the Kepler data to a simple planet interior structure model consisting of an iron core surrounded by a silicate mantle and taking flat priors on the planet mass and iron mass fraction. Here's what we obtain for the posterior distribution of the planet core mass. Essentially, we measure the planet core mass fraction to be 33 plus or minus 5% of the total planet mass. The Earth's core accounts for roughly 32% of the planet mass. So Kepler 36b is very consistent with having a flat composition. Okay. So I've described interpretation of single planet composition constraints. I think the main ideas I'd like you to take away is that due to the degeneracies, what you assume for the priors matter. Further, using the full posterior mass radius distribution to infer mass composition constraints is preferable to just point estimates. Okay, so now let's move on to planet calculations. So here, we're interested in the question of what can we learn about the underlying composition distribution of planets from this noisy set of mass radius measurements. So here, each of these planets is different but related. So this is an excellent candidate for a hierarchical modeling approach. Dan and Matthew gave us a lovely introduction to hierarchical modeling on Monday. So in the rest of my presentation, I'm not going to show any more messy integrals. Rather, I'll describe hierarchical modeling applied to this approach, the two mass radius data, in a more schematic way. Okay. So typically, when planet hunters are considering a single planet system at a time, it's common to assume effectively flat priors on the planet mass and radius, so that any mass radius pair for the planet is equally as likely or unlikely as any other. In a hierarchical approach, we open up these priors to modeling. The underlying distribution of planets might have some distribution of properties, which we can model and parameterize. Whereas some planet mass radius pairs are more likely than others, some might be completely unphysical. And so by fitting data for multiple planets together as an ensemble, along with the parameters of the population level model, we can gain insights into the composition distribution of planets. So graphically, we are represented in this way. So we have the hyperparameters for the planet mass radius or mass composition distribution, and they influence the true planet masses and radii and compositions of each planet. Here, these are essentially latent, the planet mass and radius, true planet mass and radius are essentially latent variables. And then the true properties of each planet then influence the gradient velocity and transit observations. Okay, so let me provide you with one example of this. And later in the session, Angie will present a second example of hierarchical modeling applied to planet mass radius data. But here, let me apply a hierarchical approach to try to constrain, for a given planet size, what is the fraction of planets of that radius that are rocky? To address this question, for this population statistics study, I'm going to limit the sample of mass radius measurements that I consider to have a more homogeneous sample. So here I'm just going to focus on the sample of planets detected in transit by Kepler and followed up with Keck iris to get radial velocity mass constraints. And as you can see, many of these planets just have radial velocity upper limits or non-detections, but those still contain information that constrain the compositions. And so they're fully included in this analysis. And if I were to neglect them, that would introduce biases towards higher densities. Okay. So which planets could potentially be rocky? So for that, let me draw your attention to this mass radius curve for iron core pure silicate composition. So this is essentially a rather generous lower limit on the mass of a planet of a given size that could potentially be rocky. Planets that are less dense than this definitely require some volatiles that are contributing to their transit depth, whereas planets that are more dense could be potentially comprised of iron and silicates alone. So you can already see by eye how there's, in this lower right-hand corner, an apparent paucity of high mass, high density planets. But by applying a hierarchical modeling approach, we can place that paucity on a more statistically firm footing. So here, essentially, thank you. So here, essentially, I parameterize the mass radius distribution of planets in terms of the fraction of planets of a given size that are rocky. And this model will depend on some parameters that we aim to constrain. Okay, so let me provide some results. So first, let me present results for the case where I assume that F rocky varies linearly with radius. So there's some planet size at which half the planets at that size are rocky. And then the fraction of planets that are rocky varies linearly from 0 to 1 over some radius range, here denoted by delta rocky. So here's the joint posterior probability distribution on this midpoint of the rocky non-rocky transition and the transition width. And if we look at the marginalized posterior distribution on this midpoint, we find that the 95th upper percentile lies at 1.61 radii. Now, to explore, we can sample from this posterior probability distribution on the midpoint and width of the transition to explore, to derive a posterior distribution on the fraction of planets that are rocky at any given size. And this is what I'm showing here with the color shading. So let me walk you through how to read this plot. So if you're interested in planets of a given size, say 2 or 3, then you look at a vertical slice through this diagram. Values of F rocky that are shaded red are more strongly favored by Kepler plus high-res data set, whereas values that are deep blue are disfavored. And so this blue corner in the upper right is essentially placing on a larger, stronger statistical footing that paucity of high mass, high density planets that we would see by eye in the mass radius diagram. So you can see by the time you get up to 1.6 or 3 radii, fewer than 50% of planets are rocky based on this analysis. And although this is for a particular parameterization of how F rocky varies with planet size, that conclusion was robust against all the parameterizations that I explored. And so it's the main point I hope that you take away from this analysis, and it should help to inform our interpretation of the remaining majority of Kepler planets for which we do not have mass measurements. So if we're interested in characterizing the occurrence rate of rocky planets, this might provide some guidance into the range of radii for which we should be focusing on. But it's really just the first step. We would love to know, how does the fraction of planets that are rocky at given size vary with orbital period? Is that transition gradual or abrupt? How does it depend on the post-star properties? With the current data set, we can't robustly answer these questions, and in fact, with the radial velocity and transiting data set, most of the planets that are well characterized are in orbits interior to 16 days. But let's take a moment and travel to the future and envision what the future might hold, because on the horizon, there's a whole suite of space-based transit surveys, as well as ongoing technical development of ground-based spectrographs. We can expect that the mass radius diagram of planets will continue to be populated. And so, as we obtain radial velocity follow-up for those upcoming transit discoveries, we can include the selection effects in the hierarchical analysis, but that process would become much easier with an algorithmic approach to select candidates for radial velocity follow-up. Okay. And using synthetic data to explore, to generate a synthetic simulated sample of planets, adding noise akin to the Kepler high-res sample to generate simulated measurements, which we then analyze with the same hierarchical model. We can explore how well we might be able to, what we might additionally be able to learn from gaining further mass radius measurements. And so with 50 planets, which is around the size of the current Kepler plus Keck radial velocity sample, we get approximately 40% relative uncertainty on parameters such as the relationship between the envelope mass and core mass of gaseous planets and the typical mass of rocky planets and the fraction of planets that are rocky. Whereas with 5 times more planets can do better with 10% relative uncertainty. Now, this is for an optimistic case where we're applying the same model to generate the synthetic population as we're using to analyze it, but I think it still leads me to be optimistic about the new insights we'll obtain in the future with a larger sample. Okay, so with that, I'll conclude and thank you for your attention.
Questions? I can see when I talk. Well, I think I perfectly share all what you said. There is one thing maybe you should mention also is the fact that there is the star, which bear quite a significant amount of information. So, I mean, likely some specific elements you want to study the atmosphere of the star. Could you elaborate a bit on that and how would it connect with what you said?
Sure. So, yeah, what I presented you could easily use the stellar photospheric abundances to define stronger priors on planet compositions. So Caroline Dorn has a paper describing an implementation of that. Yeah. I would caution that by applying stronger priors, you're essentially measuring with priors with a single mass radius measurement. So the precision achievable for the masses and radii of rocky planets currently are broader than the assumptions that the planet iron to silicon ratio or iron to magnesium ratio follows that of the star. So I think the approach to follow there would be to apply a hierarchical model to explore how well, based with a large sample of rocky planets, are they consistent with the planet iron to silicon bulk abundances scaling with those of the star, and can we place any constraints on the fraction of exomercury, say?
Interesting thought. So my question is, I noticed that you did not talk about the possibility of these planets have a dynamic behavior. And I was wondering, when you consider your compositions, do you ever consider that any of these planets may have geophysically dynamic, and whether models that are out there will help you constrain your degeneracy?
Are you asking for rocky planets or for planets?
What?
So these models do not include any type of explicit tidal heating with the rocky planets. In terms of mass and radius, thermal effects for rocky planets has a relatively minor effect, especially as you scale up to larger masses, superhertz. For smaller planets, it can become more important. So, yeah, I would argue at current time, that would be in the category of a feature of the models that we have less leverage to constrain for mass and radius alone. But say with secondary eclipse observations or some other additional information, that would be great to do combined.
Okay, we thank again the speaker. And we go to the next talk, Olivier Demangeon.
Hi. Okay. Hi, everybody. I'm very glad to be here and to be able to present you my work. So I will talk to you about ranking of transits, and especially of the tool that I developed for the ranking of transits, which is called BART, for Bayesian analysis for the ranking of transits. So I did this analysis with the collaboration of Pascal Bordet in Bordeaux and Maurice and Canada's. So first, let me introduce a kind of particular problematic of the ranking of transit, and I would like to do that under the light of Corot. So if you look at the transit events detected by the Corot detection tools, 98% of them end up not being due to a planetary transit. This figure is a bit pessimistic because this includes astrophysical force positive and instrumental force positive. But even if you do a more careful analysis, like the one that is being done by Magali Deleuze, and collaborators, and you try to remove as much instrumental force positive as you can, you end up with 6% of the transits that are follow-up on the ground that ends up to be due to a planetary transit. So this is very low. Just to present you the notation that I use, if it's not due to the planet where it is, so the possible scenarios are a planet around orbiting a planet star. You can, of course, as an interesting binary, another star is eclipsing the target star. And you have those two models where the target star is actually not involved in the transit, and the transit ends up to happen on a continuity. So then you can do several classes with that, especially divide them on target and then once everything, all of that is said, how do you do to disentangle the true planetary transit and the false positive? You have two main weapons, which are the follow-up observations. So there is different kinds of follow-up observation that I present here. Often to validate a planet, you need several of them, and so this weapon ends up to be costly in terms of times, of money, and then in terms of manpower too. And sometimes it's even not enough. And there is several cases where all of those observations didn't manage to secure the nature of the trend. Another important tool is a probabilistic validation tool. For example, Pastis and Blender are doing this kind of stuff. But they are costly also in their own way, especially in computer time and in manpower, because they are complicated to use and it's kind of complicated to interpret. And even with those two tools, sometimes both of them are not enough, and by nature, the probabilistic validation doesn't give a yes or no. So you have two expensive tools, and you need to carefully select at which target you will own them. And that's where the transit rankings comes into the game. It has to highlight the most promising transits, and where do you vote, and on which candidates you want to apply those two tools. So it's with that in mind that we decided to develop BART. And when you develop the ranking tools, you don't want a big machine, you don't want an expensive machine, you want something that is quick as possible, as automated as possible, and the bonus if you can apply it to different types of data from different instruments. And so in order to make this tool as quick as possible, we decided to reduce the amount of data that we put in for each candidate. And so what we did is instead of using the light curve, we used some measurements that are made on the light curve. And so we measured the period, the depth of the even and odd transits, the depth of the secondary eclipse, which is measured at the phase 0.5, and for the shape of the transit, we use the linear and outer duration. To analyze those data, we use simple models. We use circular orbits, and here I listed all the parameters: the period, the radius ratio, the effective temperature ratio, the impact parameter, stellar density, and the contamination parameter. To link those two things, the data and the models, and to produce the ranking, we rely on the determination of the probability of the planetary hypothesis, and for that we use Bayesian framework, of course, with Bayesian model comparison. For your information to compute the probability, we use a kind of simple tool, which is the Monte Carlo integration. And before this Monte Carlo integration, we want to narrow down the parameter space. And to do that, we use an MCMC sampling. MCMC sampling is not necessarily something that is automated, and we want something that is automated. And so what we did is start from the automatic metropolis-Hastings algorithm developed by Gregory in 2005, and we adapted using the correlation information of the traces to perform better in a correlated parameter space, which is obviously the case of transit model. And so then let me jump to the first result. So as I said, this tool has been developed primarily for Corot, and so we applied it to a set of 22 candidates from the LRC02 field of Corot. And here are the results. In this subset of candidates, you have 5 confirmed planets, 6 identified false positive, and 11 in result case. And the result, the main result of BART doesn't take a lot of place in this table, but it's on the first 2 columns. So what we wanted is this ranked candidate list. On the third column, you have the nature as derived by the Corot detection and follow-up group. This is the nature derived by BART, and when I say nature derived by BART, it means the models that have the highest probability. And here are the probabilities of the different models. So first, what I want to remind is that these probabilities are an informative tool that you can use to optimize your follow-up. And because if you think a priori or with the help of these tools that your candidate is a planet, or if you think it's a contaminating object, you will not use the same follow-up observation. So this is really to help you for the follow-up. This is not a probabilistic validation tool because the models are too simple, the data set is simplified. So this is really to help and to optimize the follow-up. Then let's focus a bit more on the results obtained for the planet. The candidates that we know are planets. The first interesting thing is that most of them are in the first half of the ranking. And 2 of them, Core 6 and Core 25 are well identified by BART and are on the top 3 rank. So this is great. This is exactly what we wanted. For Core 11, it's in the middle of the ranking. It's not very satisfying, completely satisfying, but you know why. This guy has an elevated impact parameter, so the transit is a bit V-shaped, it's rounded, so it's a bit difficult to estimate the duration, the duration. For Core 26B, it's also a kind of particular case because the star is a ball, it has an unusually low density, and so BART interprets this low density as a sign of binary, eclipsing binary. Core 22, if German 2 is in the room, she can attest that this is a very complicated case. It's not possible to confirm it by follow-up observation, and so it has been confirmed by pastis, but it requires a lot of time and a lot of effort to manage to do that with pastis. So it's not surprising that it's ended up to be in the middle of the rank. For the false positive, the very good news is that there is no false positive for BART in the sense that none of this known false positive has been identified as a planetary system. But more than that, the important result is that most of them are on the second half of the ranking. And another thing is that the only misinterpretation that BART produces for this. This is really encouraging. This is really good results. I will go quickly on that. For the unresolved cases, BART detected 2 very interesting guys, especially this one, but sadly it's too faint to be followed up. And so recently we applied this tool to K2 candidates. So we decided to apply it first to the candidate list analyzing Montaigne, which are from the Camp 1 data of K2. There is a lot to say about that. I have a few time to discuss about it, so I just wanted to highlight something that I thought was important. So the first is that you can be a bit puzzled by the fact that the first 2 guys are marked as false positive by Montaigne operators. And this is due to the fact that they detected a secondary eclipse that we didn't detect. So this can be due to the fact that navigation for K2 is a bit tricky. We know that, or the fact that we assume circular orbits of BART we didn't look for the secondary eclipse where we should have. I will skip this guy. You have those 2 candidates that are very interesting for me. Why? Because I was the author of the 2 analyses made for this system. So these guys belong to the same system. And what is very interesting is that they are very close. It is 2-planet system, very close to the 32 mean motion resonance. And so close that you happen to have simultaneous transit. So you have the transit of the planet B and the planet C that overlap on the black transit curves. And that's why when you try to blindly evaluate the even and odd transit curves, you make some mistakes, and this is why you have the planet B there. Another good thing for the ranking is that one of the first planets detected by K2, which is in the Prospect system, is there well identified. So to conclude, the first results are very promising. It's already an improvement compared to the ranking that has been done by Coron, in the sense that it was relying on independent tests. So most of the measurements that we made on the last year are very similar to the tests that were done. But BART automatically take into account the correlation between those tests, and it takes a couple of minutes to analyze the candidates. What I didn't have to look at in depth is how the parameter inference that is done during the NCNC exploration can help for the follow-up strategy. I think this is a very important feature of BART. There is some limitations that are clearly identified, and this is good because there is some way to improve significantly. I show some limited testing, and of course, the second step is in-depth testing. This figure where you have in light green the Corot candidate, you can see 600, more than 600 candidates. Of course, there is also the Kepler candidate and the K2 candidate, so there is lots of improvement in terms of testing. The next step is also, of course, to try to see if, including the complexity of the model, we can improve the result without losing in terms of quickness of the tool and automatization of the tool. And of course, the final objective, the Olympic Games, will be for test and plateau to see how this tool can. Thank you. And,
Thank you. A question?
Hi, so I'm a little bit worried about this assumption of circularity. So about half of all exoplanets with known eccentricities exceed 0.2 eccentricity, which doesn't seem that high, but that's enough to change the apparent cell density by a factor of 2 that you observe from the concept. So you can easily imagine that those objects are being killed in your analysis. They're real planets, but they're just slightly eccentric.
I fully agree with that. So this was a starting hypothesis because we were a bit worried that the eccentricity include lots of correlation that we will not be able to automatically sample the parameter space very well if we had the eccentricity parameters. But now I think that there is some way to do it. I completely agree with you. We need to take into account the eccentricity. We do it. And I think there is ways to do that.
Okay, I'm afraid there is no time for other questions. We thank again the speaker. And we go to the next presentation by Rodrigo Díaz.
Aloha to the guys in there.
And he will speak about validation of quantity planet candidates.
Hello, good morning. I'd like to start by thanking the organizers for the opportunity to be here today to discuss plant validation. So for those who are not familiar, plant validation is a technique that allows us to secure the planetary nature of transiting candidates, not by measuring the dynamical mass of the transiting object, but rather by accumulating enough statistical evidence for the planetary hypothesis with respect to other false positive hypotheses. So why is this necessary? Well, the fact is that for most Kepler candidates, we've seen these candidates already many times, but here they are plotted with respect to the expected radial velocity semi-amplitude, and you can see that most of them would produce radial velocity amplitudes of the order of a meter per second, which is extremely hard for these faint stars. And so we cannot measure mass easily. And we know that inside here there will lurk many nasty false positives that we cannot identify easily. And of course, what people have done to deal with this is to estimate the global false positive probability, as done in the famous paper by Morton and Johnson, and then use that or other estimates to conclude an argument that the false positive probability is negligible with respect to other error terms in their planet inference analysis. But if we want to push a bit further, we'd have to actually solve some of these candidates, and this is where planet validation comes to the rescue. So I would argue that there's an interest in measuring the distribution of false positives through the radius period diagram to include it in the different types of planet of population retrieval analysis we've seen earlier this week, and also to be able to correctly propagate the error bars, which apply to any method doing this type of analysis. Planet validation, of course, is also interesting to secure the nature of individual objects which are particularly interested, such as habitable zone planets. So to put this in a more in a more formal stand, let me say that the validation of a transiting candidate can be cast as a Bayesian model comparison problem, where we have two hypotheses, the planned hypothesis and false positive hypothesis, and they're both competing for support for the data. Of course, what you need to do is to compute this ratio called the odds ratio, is just the ratio of the posterior probabilities for each hypothesis, which turns out to be the base factor of the ratio of the marginal likelihoods or evidences. Important things have many names, so I'm okay with this having many different names, times the prior odds, which depends on our current knowledge. And of course, the base factor is contains all the information the data provides on this issue. All right. So once we have computed this, the posterior ratio could be the odds ratio can be used to as an input for planned occurrence estimators to produce a more robust analysis. So let's go a bit into this term here, the false positive hypothesis. Actually, this is, as we have just seen, just a term of, it's a sum, it's a probabilistic sum of different terms coming from different scenarios, astrophysical scenarios that can mimic a transit. And of course, here there's a few of them. This is particularly nasty because it's in the same system as the target star, so you won't get any standpoint effect on one of these. But there are many others which come to mind, and why not adding them all, adding them all up? So I have divided this notation for false positives based on the Feynman diagrams of quantum electrodynamics, which is quite simple actually, but I don't have time to explain it here, but I will just show this as a teaser for tomorrow's hack session, so be here for that if you're interested. And you can, just as the Feynman diagrams, use this notation to convince yourself of which are the important terms in your summation. And it turns out that for one transiting object, this sum can be approximated as these four false positives, which is the triple hierarchical triple, a planetary in a planet in a binary, and the two background systems. All right. So once we have convinced ourselves of this, we can start actually validating. And I would like to speak a bit about Blender, which is of course the big name in the game. It's a tool that was used, but that is actually used by the Kepler team to validate most of their small transiting candidates. And and this is in the Blender tool is done by computing the delta chi-square based on the Kepler light curves between the planetary hypothesis and the false positive hypothesis. That this is what you see in the black and red contours there, and using additional measurements to rule out additional regions of parameter space. Here you have the Spitzer light curve, which kills all this part of the diagram, spectroscopy, color information, and what you finally get is this allowed region, which encompasses stars which are between 2 and 4 magnitudes fainter than the target star, and then you can use galactic models to count how many stars fall in there and also in the line of sight of the target, and then compute the probability. And this is how it's done. Just one thing I want to mention about this is that by catching this in a very strict way, it's at least worrying, based on this figure from a paper by Phil Gregory, where you can see that the most of the contribution to the marginal likelihood comes from the outer regions of the posterior distribution, and this is just because the volume is much larger. So this is at least worrying about the way to do this. Another technique that's been put forward, developed by Tim Morton, it's called BALFAST, and it's very clever. It produces a population of false positives based on galactic models and physical models, and bets, it includes some betos on those prior false positives based on additional measurements. Again, this is once again a yes/no betting, and then computes the trapezoidal model for the light curve, And it uses the same physical model for all false positive scenarios and the transit and the planet scenario. So the likelihood function is the same for all hypotheses. And you can see it here as a red point for the different scenarios, which is exactly in the same position. So then the overlap between the likelihood and the prior can be marginalized and to get a probability. Of course, one of the best things about this is that it's really fast. Unlike Bastis, which is has a very detailed physical models and has also been developed together with Almenara and Santern with the idea in mind to model all data together, not the likelihood on one side and then the additional observations on the other side, but taking everything together, doing physical models which are different from between the false positives and the planet, and then running everything. I will not explain in detail as I will speak tomorrow during the hack day, but basically what Bastis does is produce the full parameter posterior of the different false positive scenarios, and then estimate from there the Bayes factor, which is admittedly a very hard problem, and I could speak for another 15 or 30 minutes just about this arrow here. The point is that you can get the odds ratio this way. Instead of boring you this, I will just show that in the case of this target, where we have, which was also modeled by Bastis, without the spectroscopy constraint, we can see that the allowed region is compatible, but we've obtained it self-consistently. All right, so with this I would like to jump to some results. First is Corot 22, which was already mentioned in the previous talk. It's a 4.9 Earth radius planet discovered by the Corot mission. So here you can see that all the datasets that were fit by Bastis, that were modeled by Bastis. So you have the radial velocity as a function of time, radial velocity as a function of orbital phase, the three Corot color bands, and the entire orbital photometry of Corot, together with some broadband photometry. And in this plot, each color corresponds to a different false positive scenario. And what you get in the end is the Bayes factor. The Bayes factor for each different scenario. 2 minutes. Yeah. And the areas here are it's an area of uncertainty. So let's say that when the Bayes factor is above this value, then it's support for the planetary hypothesis. You can combine everything and get the Bayes factor or the odds ratio of the planet with respect to any false positive scenario. And if you convince yourself that that you have explored all relevant false positives, you get the posterior distribution for the planetary hypothesis, which in this case fits at very high values. So this is what we call a validation of the planet. And in the mass radius diagram, this looks like this: radius and no mass. So to finish, I would like to discuss another case we have explored with Bastis. It's Kepler 22, a 2.4 Earth radius planet in the habitable zone of its star. And once again, I'll show you a similar plot with the data set. So you have the Kepler transit light curve, the Spitzer transit light curve, which clearly rejects the triple scenario, and the entire orbital photometry of Kepler. But you can see here there's a green arrow at around phase 0.5, which I'll zoom on. It's a small bump, which is caught very well by the background eclipsing binary scenario. And this leads, of course, to a very strong support for the background eclipsing binary scenario, which here has Bayes factors below 1, meaning it's a support for the false positive scenario. Of course, when we first saw this, we were sort of worried and excited at the same time. But when we looked into a bit more detail and we plot the secondary phases for the 5 different epochs we have the Kepler observed this object, we see that epoch 1 has a hole and it's kind of a flux fall down here and something happening here as well, which is actually producing this bump. So once we take this away or we filter in a stronger way the lighter, we recover the planetary hypothesis as the most probable one, which is of course something to think about. So with this, I'll jump to my summary. I'll say that quantum validation is not easy, but it's definitely worth it and necessary if we want to move forward in our planet occurrences analysis. And it could provide very important information for different techniques. And it's essentially a Bayesian model comparison problem, although different approaches have been taken in the past. And the future directions, given the Kepler 22 example, is of course would be to include more sophisticated noise models. So we do not have to filter our lighter very strongly, or use just the transit part, and account for the different correlations in the lighter in a robust way. And also, of course, as Eric Ford mentioned in the first day, it's a matter of efficiency in the sampling algorithms, which is putting a lot of effort on our algorithms. And then, of course, a final point would be to better understand the evidence estimation techniques, which is also something I have not discussed, but it's a bottleneck of these techniques. All right, so with this, I'm finished, and I will gladly answer any question. Thank you very much for your attention.
Thank you. Questions?
I think I disagree that if you want to get the plant population statistic, plant validation is necessary. But anything that you need, if you're only interested in statistics, is you need to know how many signals are being produced by those constants.
That's what I'm talking about.
You don't have to specify for each and every event which one has the planet or not. You just have to subtract the false positive background.
Of course, but maybe I did not express myself correctly. That's what I had in mind, not to run this on every single Kepler candidate, but to obtain the distribution of false positives correctly. So what the input to your model is not like a flat in log as we learned on Monday, but rather a more informed distribution. Does that make any sense? Let's discuss about that. All right.
Okay, another question?
So the blip at phase of 0.5 exactly causing a large favor towards the background protein binding model. Does that say, are you restricting eccentricity equal 0, or like why, because I would just expect a 200-day protein binary to have exactly 0 eccentricity, so why would that?
The model is not restricting for eccentricity, and actually if you take a closer look, it's not exactly at 0.5, but rather at 0.51.
Right.
But in any case, no, we are not doing that. I guess it's just a problem of the noise model, which considers these as significant. The noise model should be improved so that this becomes just a bound. Right? But I know this has been the case also for some blender validation. I think it's Kepler 61. One of the planets in Kepler 61 has the same issue, and it's being validated conditional to the fact that this is not secondary.
Okay, let us thank again the speaker, and we go to the next speaker, Angie Wolfgang.
So we've been here for an hour and a half so far. My butt is hurting. Everyone please just stand up and shake out while I say hi to the internet, and then we'll sit down and go on to my talk. Thanks. Hi, internet. All right, great. So my name is Angie Wolfgang. I just graduated, I just defended at UC Santa Cruz. I'm moving to Penn State in a couple weeks, taking an NSF postdoc fellowship there. So today, I'm going to talk about a project that I did with Eric Ford and Leslie Rogers. Again, this is a practical example of how you apply hierarchical Bayesian modeling to a question that is very relevant for all of us in the room. Okay. So Leslie gave an amazing overview of what you can do individually with planet mass and radius, especially for the sub-Neptune class of planets. So just to remind you that I've thrown this up here, that this issue of compositions can be constrained, but of course there are degeneracies, by mass and radius. And this is one of the very hot topics right now in exoplanet science, is to do this. But again, as we also just heard, masses are not going to be measured for the vast majority of Kepler planets. So the run-of-the-mill Kepler planet, the host stars is simply too faint for radial velocity follow-up, and transit timing variations require an orbital architecture that has more than one planet in it and is close to resonance. So we're just not going to have mass measurements for the run-of-the-mill Kepler planet candidate. So what we need, there's a niche here for us to fill. We need to have a statistical mass-radius relationship so that we can do some science with that run-of-the-mill planet candidate. So the idea here is to take the observed masses, the planets with observed masses and radii, and fit some sort of distribution that represents the underlying joint mass-radius distribution to it, and then use this distribution in order to predict a mass given the radius that has been measured by Kepler. All right, so this has a whole host of applications. This mass-radius relationship thing is extremely relevant. So on the observational side, it's needed in order to compare transit and RV detection. So if you want to do occurrence rate stuff that crosses different surveys, you need, especially transit and RV surveys, you need this mass-radius relationship. If you are interested in studying the dynamics of the entire Kepler planet population, you also need this, because mass is the physically relevant quantity there. And similarly, if you're interested in studying the formation of Kepler systems, you need a way to get the masses, which is the physically relevant quantity often for these planet population synthesis and other formation processes studies. Okay, so there's a little bit of a wrench that gets thrown in this mass-radius relationship. And it comes from, again, taking this population-wide view, right? It's a very realistic expectation that there will be a distribution of compositions within the population. Now, in a paper with Eric Lopez, we showed that if you do assume this distribution, if you fit for the distribution, you will get out a mass-radius relationship that has some intrinsic spread in this relationship. All right, so from the get-go, this mass-radius relationship we expect needs to have some sort of parameterization that accounts for this intrinsic spread. Okay, so this is kind of more on the theory side. Observationally, oh right, so this is just a point that let me explain what I did here. So we fit for the composition distribution using the radius distribution as our observable, and then generated a population of planets based on that composition distribution, which is the mass-radius relationship that you see here. So for any given radius, there is a wide range of masses. That's the point that I'm making there. Okay, so observationally, people have expended a large amount of energy and time and effort to follow up the planets that do host, that do orbit bright stars. So this is some observations from the radial velocity follow-up of the Kepler planet candidates. And so one of the first things that you can, so this is also one of the mass-radius relationships that was fit to that data. Now, the very first thing that you can see from the observation itself that there is some intrinsic spread. Now, of course, there is extreme uncertainties on these measurements too, and they're not plotted here. But just to give you a sense, they can be as large as that red arrow. So if you just look at the point estimates, it really does look like there's intrinsic spread. But when you start to think and take into account the measurement uncertainties, you might not necessarily be convinced from that just based on the observations. All right, so that was part of our goal in doing this. We expected there to be an intrinsic spread, but we wanted to make sure the data was actually saying that. Okay. So now the question becomes, how exactly do we incorporate this dispersion, right? So we start out with this deterministic relationship here, where we have, it's described by two parameters, C, the normalization constant, the power law index. This, when it's fed to the data using our very familiar technique of weighted least squares, what it's really doing is representing the mean relationship, the mean mass radius relationship. And so what we want to do is get that intrinsic spread. So realizing that this deterministic relation can be interpreted as a mean relation, then we just put that as the mean of a normal distribution where we also fit for the intrinsic spread in this normal distribution. Okay. So this is the key to going from the deterministic relationship to the probabilistic relationship. Where now, instead of having one-to-one values, we now have a probability density function at any given radius that describes the range of possible masses that a planet may have. All right, so looking at the practicality of the issue here, we have, again, large mass radius uncertainties, and these parameters describe the entire population, right? They don't, so those are the things that we're interested in. This is exactly the situation that we want, that we need to use hierarchical inference for. All right, so we've heard a description of what hierarchical Bayesian modeling is from 4 different people this meeting so far. I think that's great because the more that you hear different explanations, the better, the higher the chances are that one of them might sink in. So really quickly, I'm going to give you my interpretation of this. All right, so starting from regular Bayes, we have the posterior, the likelihood, and prior. You can write Bayes' theorem in terms of this graphical model, all right, and where we have the parameters relating to the observables in a probabilistic way. All right, so Dan flashed this up as this following cartoon. We have physics and the data. All right, I don't know about you, but for me, I don't really understand something, a cartoon that kind of looks like a black box to me, unless I really dig down into the details and try to tease everything apart. So that's what I did in my first paper, where I looked at the composition distribution. I'm not going to explain this, I'm just throwing this up here. This is what a real life example of that kind of cartoon can look like for a problem. All right, so there's a lot of work that goes into going from this cartoon to something that's realistic for your problem. All right, now to make the key step to hierarchical Bayesian modeling from quote-unquote regular Bayes. So this is the key question. What if there isn't just one true value of a parameter for all of the individuals in your population? So an example of compositions, you don't expect every single planet to have the exact same composition. You expect that there is an intrinsic distribution of that. And you want to understand what that intrinsic distribution is. It happens a lot for population studies. So you're going to see HBM, hierarchical Bayesian modeling, a lot come up in future population studies. Okay, so in order to account for this intrinsic distribution, all that we do is we take regular Bayes and we apply conditional probability to it. So we still have the posterior, the likelihood, and now we have the prior, which has incorporated this intrinsic distribution of the theta values, the parameters, given another set of parameters called the hyperparameters that describe the population. All right, graphically, this is what we have. So now we have the population-wide parameters, the individual parameters, which Leslie called weight variables. So we don't actually observe these. So this is something like the true mass of the planet, and then the actual observables. All right. So again, this is the physics that we're interested in, and then this is the data. All right. The beauty of this is that you can still use Markov chain Monte Carlo, and you can think about this as just adding another layer of probabilistic structure. In practice, things are a little more difficult. All right. So now this is the mass radius relation that we want to fit. So we have 3 parameters. This is the graphical model for the situation at hand. So the data here is actually the flux versus time and the radial velocity versus time. But in practice, what we don't have access to this information for this project. We use the radius, the observed radius and observed mass that the observers have given us. All right, and so in making this simplifying assumption, we've glossed over a lot of structure that is in a joint probability distribution. So the key thing, the key thing here is that observers who meet your likelihood, please publish your posterior samples and products so that we can incorporate them into this kind of hierarchical modeling. All right, so results. Here we have the posterior distributions for these hyperparameters that describe the population. So this is just showing the constant power law index. Here, this is the key point on the right side. So when you explicitly incorporate this dispersion parameter, you see that the data very strongly disfavor 0. Now, note about the prior that we used. We used a prior that's very strongly weighted towards 0. Right? So this is definitely not reflecting the prior that we used. The data is telling us that there is intrinsic dispersion. All right? So we have to, an accurate mass radius relation must reflect this. Okay, I don't quite have a lot of time to go into the details, but when I was presenting preliminary results from this, a lot of people were asking me, well, what if you change the data set? What if you change the radius range over which you vary? And so this is just showing the posteriors that we get when we do change some of those assumptions. So you can see that there is a offset in the parameter values that we infer if you use only RV data or only TTV data. And this is also what you get when you change the range of radii over which you consider. So 1 to 1.6, 1 to 4, and 1 to 8. All right, so the key thing here, I'm just drilling home, is that only the smallest planets don't require an intrinsic dispersion to accurately describe the mass radius relationship. All right, so this is the MR relation that you should be using from now on. This is what it actually looks like with the data. All right, one last comment. Right, so for individual planets, if you don't have a mass measurement, you can use the probabilistic mass radius relation to constrain the composition. So I have some code up on GitHub to do this. So if you're interested in an individual planet, you don't have a mass measurement for it, you can download that and talk to me. So the case study here is Kepler 452b. Now this planet has generated a lot of interest, a lot of discussion. So I want to clarify what we actually did in our analysis in our paper, all right? So here we have the joint mass radius distribution. Well, the input into this is the radius distribution that you see at the top here, all right? So that's from stellar parameter modeling and transit modeling. You can input that distribution into this mass radius relationship, you get the joint distribution. And for every individual sample, you can analyze whether or not that is consistent with the density that is denser than 100% silicate, aka rocky. All right, so when we do this, the fraction of these samples that fall in this rocky regime is just about 50%. Okay, so a lot of the media didn't quite grasp this very important qualification. So a lot of people were pointing to, and rightly so, to Leslie's papers, which she just presented to us, that most 1.6 Earth planets, Earth radii planets are not rocky. So I just want to point out that we are fully consistent with her paper. And that the key is that 452b is not conclusively rocky. It's just a 50% chance that it is. All right, so I'm going to throw up some future work. If you want to check out more of the details, look on the archive, and thank you very much.
Thank you. Questions?
Thank you. Concerning the different posteriors, when you get different populations, of course, you're not correcting for biases or incompleteness, right? So you think that's, which one?
Two. Yeah.
Right.
Yeah,
okay.
that is
so it's not, you don't think it's significant, right?
Oh, no. Okay. I very much think it is very significant. The key thing here is that all right, so we have to start somewhere with this kind of thing. So I know Leslie is working on thinking really hard about the selection effects. We definitely think that is important. We wanted to have a mass radius relationship out there that at least incorporated some intrinsic spread. So that was our goal in doing this, is to characterize the intrinsic spread, even knowing that it's probably going to be biased by the selected biases.
I meant that the difference was not significant,
Oh.
not the selected
Okay, another question, maybe previously naive, but I just want to make sure I got it right. When you get a mass or size, and practically this is a statistical distribution, highly biases, skew very likely is going to zero most of the time. Most of this mass goes to zero. And there's a solution, you can get a 3 sigma solution to zero mass. So do you account for that in the scheme?
Yeah,
or,
so
what kind of profile do you use? Because this is never published, absolutely right. So what do you do practically?
Yeah, so practically what we ended up doing was using a normal distribution, which is the exact same assumption that you're making when you use chi-square to the mass radius relationship. But yeah, you bring up a great point. Please publish your mass posteriors, especially the joint distribution, because we want to incorporate the skewness into this kind of measurement and to improve this for everyone. So please publish. Thank you.
Last quick question.
This may be somewhat naive on the statistical side. When you're looking at this idea that there's this intrinsic population, there's a spread. Are there particular constraints that's assuming about what kind of spread it is in terms of can it be two distinct populations or something like that?
Yeah, so that's an important caveat that I listed here at the top. So the model that we use has this intrinsic spread as being constant over the entire radius range. So it is not incorporating any kind of assumptions about how many populations there are, like subpopulations there are. There's a lot of work that me, Leslie, anyone can take this framework and run with it and see what needs to happen. But the key here is once we get started in analyzing more complicated mass radius relationships, we really need to quantitatively compare them, which requires calculating basic evidence. So that's the little bit of work that needs to be done.
Okay, let us thank again the speaker and Ruth Angus.
Hello everyone, I'm Ruth Angus. Okay, thank you very much for having me here. Just to give a little bit of motivation for why I'm going to talk about stellar rotation periods. If you're interested in exoplanets, you should be interested in stellar rotation periods, because rotation periods tell us about the host star, they tell us about the age, they tell us about the activity, so they tell us what environment the exoplanet is living in. And also, if you have graded velocity observations, you really want to know the rotation period of your host star, because activity signals can masquerade as exoplanets. Okay, so this is a Kepler light curve from Kepler 452. And with Kepler, for the first time, we're actually able to measure rotation periods from light curves because of the incredibly high precision. So this just shows the variation, sinusoidal variation, over time that's produced by star spots and active regions that transit the surface of the star once through rotation period. Now, I just said sinusoidal variation. I did not mean to say sinusoidal variation. That was a very inappropriate slip of the tongue, because I'm going to right now go on to say that it's not sinusoidal at all. So standard practice for measuring rotation periods is to use a periodogram or an autocorrelation function. Both of these methods have been very successful, provided us with lots of rotation periods in the past. But a periodogram, a sign-fitting periodogram, is not necessarily the best thing you can do, because, as I just said, this kind of variation is not typically sinusoidal. So a sine wave is not a good generative model for a stellar rotation light curve. An autocorrelation function is perhaps a little bit of an improvement on a periodogram, because it doesn't matter what functional form your light curve is, it just matters that it's periodic. It's just comparing the light curve to itself at a range of lags. So it can have any shape, as long as it's periodic, we find the period. However, it's not very easy to quantify uncertainties that you get from autocorrelation functions because an autocorrelation function isn't a generative model. So let's go back to the light curve. And something that you'll notice is that there's some smoothness here. We know that there's some smoothness in our light curve that's produced by stellar rotation. And another way of saying that is that there's correlation between your data points. Each data point in your light curve knows something about the other data points that are nearby it, and they are constrained to be similar to those other data points. This makes stellar rotation an ideal case for using a Gaussian process. So we've already had a bit of an explanation of Gaussian processes from Tom Evans, and we're going to have some more, I think, from Neil Gibson later. So in brief, a Gaussian process is absolutely perfect for describing a quasi-periodic, non-sinusoidal signal. The formal definition of a Gaussian process is a Gaussian process produces a data set which has a probability distribution that looks like a multivariate Gaussian, where the number of dimensions of a Gaussian is equal to the number of data points. But usefully, it can be thought of as a distribution over functions. So if you have some function and you don't know the exact functional form that you should use, you can remain agnostic by using a Gaussian process. It's also a semi-parametric model. It's also a nice way to reduce the number of dimensions of your problem sometimes. So, as I said, there's correlation between these data points. There's some covariance. You might be able to describe that covariance like this. This is a covariance matrix that might describe a stellar light curve. You've got the brighter regions represent high correlation, and the darker regions represent lower correlation. So data points that are close to each other are highly correlated. Data points that are far away from each other are less highly correlated. This covariance matrix can be parameterized by kernel function. So this function produces the covariance matrix that I just showed you. Each element in that matrix can be represented by this function, where you have, in the exponent, you have the distance between data points, and you have a length scale, which describes the rate of fall off of your correlation. So if L is large, 2 points that are very far away know a little bit about each other, and if L is small, only points that are close together know about each other. This is a very useful and very common covariance kernel function that is used very often. It's very exponential because it's a very simple thing that you can write down. There's just 2 big parameters there. For stellar rotation, we use the quasi-periodic kernel function, which looks a little bit like this, or exactly like this. This is the squared exponential kernel function that I just showed. We're multiplying it by the periodic kernel function. This kernel function has 4 free parameters, and this is the parameter that we're interested in. That is the period. It produces a covariance kernel that looks a little bit like this. So you can see that there's some periodic structure here. So 2 points that are separated by 1 period will be correlated. 2 points that are separated by something that's not the period will be less correlated. And then that correlation falls off as a squared exponential. These are some draws from this covariance matrix. And I'm varying the hyperparameters over these draws so you can sort of see the different kinds of functions that you can get. But you can really see that each one of these looks quite a lot like the sort of light curve you see in a star with spots. So this is a great model for light curves. I said P is the parameter that we're interested in. It's just, these are called hyperparameters often. They're just parameters. We can sample from their posterior distributions, and that's exactly what I do. In order to sample from the posterior, I need a likelihood function. And here, I just want to convince you that using a Gaussian process is almost exactly the same as everything that you've done up until now. This is a vanilla Gaussian log likelihood function. It's also known as minus a half times chi squared. This can be written This way is matrix notation. So here R is your residual vector. It's all of your y's minus your mean model. And C is your covariance matrix, which if you're using this, you are implicitly assuming you have Gaussian white noise. If you want to not make that assumption and use correlated noise, a Gaussian process, you just replace C for your parameterized covariance matrix, and it's exactly the same. Okay, so to test this method of using Gaussian processes to measure stellar rotation periods, I generated some fake light curves, some stars with spots, and I tried to recover the rotation periods of those light curves. I used 3 different methods. I used the autocorrelation function method, the periodogram method, and a Gaussian process method. So here are some results. This shows measured period versus true period. And you can see the one-to-one line here that's black and dotted. And you can see that our recovered periods from the autocorrelation function are precise but not very accurate. Now we think we know the reason for this. We think this is because if you try to measure the position of a peak, where you're measuring a peak that's superimposed on a decaying, an exponential decay, you'll measure a position for the peak which is a little bit short. So you'll consistently measure a period that is too short. If you use the autocorrelation function method naively without modeling this exponential decay. So that is one other drawback of the autocorrelation function. You have to treat this quite carefully.
2 minutes.
So periodogram results. This is the exact opposite. These results are accurate but not very precise. And finally, the Gaussian process results. You can see that these are both accurate and precise. So I think this shows that the Gaussian process method is doing incredibly well. And the only drawback of the Gaussian process method is that it does take a long time. So each one of these stars, I measured the rotation period using NCMC. I used NC, the package by Díaz and each one of those steps you have to convert the covariance matrix, so it takes a long time. However, if you're interested in a small number of stars, or you have a small number of data points, or you're happy to do something like binning, then using a Gaussian process to measure your rotation period can be tractable. And just to show all 3 results alongside each other, you can really see that the Gaussian process results align very tightly on this line. Periodogram results not so much, and the autocorrelation function results are a little bit below it. If you're interested in using Gaussian processes to measure rotation periods, my code is on GitHub. So please go ahead and have a look at this repository. And just to summarize, the negative side of using a Gaussian process is computation time. However, there's a lovely package called George, also written by Dan Formanaki, that really speeds up the process, and I wouldn't have been able to do that analysis if I didn't have something like George. Also, you're making an assumption. You're making an assumption that your data are Gaussian distributed. If they are not Gaussian distributed, then you can't use the Gaussian process. In most cases, it's a decent enough assumption that your data are distributed, but outliers can actually affect your results. However, on the positive side, you might be getting some more accurate periods, you'll definitely be getting more representative uncertainties, and you can directly use your posterior samples for whichever your favorite hierarchical inference problem is. If you're interested in applications for using posterior samples of rotation periods in hierarchical inference, come and see my talk at 2:40 in session 13, where I'll be talking about gyro chronology. That's what I want to say for now, though. Thank you.
Thank you very much.
I could also say that another disadvantage of this technique is that the choice of the correlation function is rather arbitrary. you demonstrated some functional formula for the correlation function. But the question is, how did you where did you obtain this formula? The second question is why you don't have negate correlation in this model?
So the question was, yes, why do we choose this function? We chose it because we understand a little bit about what sort of shape we're expecting from our stellar light curves. So we expect that there is some correlation on the rotation period timescale. We expect that after a few rotation periods, that correlation is going to go down. So that kind of naturally provokes the use of the squared exponential multiplied by the sinusoidal exponential. We could have chosen to use a squared exponential multiplied by a cosine kernel, in which case you can have negative correlation. However, for stellar light curves, you quite often see multiple peaks per rotation period because you have more than one active region on the surface of your star. So you need for there to be allowed to be some correlation in the intra-period domain as well. Yeah, I hope that makes sense. If we were going to really test the choice of covariance kernel, we could do some model comparison. And perhaps that's something that we'll do in the future. But Gaussian processes are expensive. Doing an MCNC with Gaussian processes is even more expensive. And calculating a marginalized likelihood with Gaussian process using MCNC is extremely expensive. So I think you need a really good reason to want to go and do it. Maybe you're not satisfied with that answer and we can talk a bit later.
I think you might have just answered my question as well, but all of the kernels you've discussed produce C infinity in continuous differential processes. Have you considered ones that produce less smooth processes?
Like a return or something. Yeah, we could. This is kind of still work in progress. And these results are fairly new actually. I am at the moment I'm happy with the choice of kernel that I'm using because I think that it's actually really nailing down that period. Like you can see, it's really getting it. And as long as we're marginalizing over the other hyperparameters and we're focusing on rotation period, I think that's the important thing. So I'm not hugely motivated to play around with other covariance kernels too much, but even something like a 10, and seeing what difference that brings, I think will be interesting as well.
So one more question.
You discussed quite extensively how accurate the period results are and precise. But in your frame, I kindly answer the question, given the light curve, is there a periodic signal in there?
Okay. So this is another motivation for why I wanted to do this analysis at all. At the moment, it's like when people report rotation periods, it's like a binary thing. There is a rotation period that we're confident is this rotation period, we definitely see it, or nothing, we're not going to report anything. So the nice thing about this framework is that it would allow you to compare for example, periodic Gaussian covariance kernel versus a completely non-periodic squared exponential kernel function. You could do that test and you could figure out, you could do model comparison and figure out is there support in the data for a rotation period or not. So that's another advantage of this technique, is that you can actually say something about that.
Okay, a really last question.
It's about pointing up there, no outliers. Do you think there's any chance to come up with a kernel that considers outliers?
So there are other processes that you can go with. There are Dirichlet processes and Poisson processes. And so there are other functions that you can use which have more power in the tails. I haven't personally done anything with those, and I think if you want speed, then making the assumption that, if you just have a few outliers, you'll be alright using a Gaussian process. You can make the decision yourself about what to do with those outliers. If outliers really are a problem, then I think if you want to do something fast, you might just not be able to do it without some process or something like that.
Okay, let us thank Ruth Angus again for the very nice talk. Thank you.